Hi everybody. This video is going to be on section 4.6, bases and dimension. So definition. A set of vectors v1 all the way to vk in a vector space, V is called a basis for V so two things have to be true in order for a set of vectors to be called a basis. First, the vectors are linearly independent, and B, the vectors span the whole space V. Okay? Now, something to note here, just for vocabulary's sake, we say basis when we're talking about one, but we write bases with an E if we're talking about more than one. So note, bases is the plural of basis. Okay? So important thing to know just for the sake of vocabulary. So again, a basis is a set of vectors that are linearly independent and that also span the entire vector space. Another note. A basis is the same as a minimum spanning set. Okay. Actually, we called this did we call it a minimal? Yeah, let me write that down correctly. A minimal spanning set. Minimal spanning set. Okay, so let's talk about the primary example here for Rn, because Rn is what we always look at. So we know that the span of I and j gives us all of R2, right? Also, I and j are linearly independent. And so what does that mean? This means that I and j form a basis for R2. Now, I and j really are the vectors 1, 0 and 0, 1, right? And so for R3, we could have the same thing, right? IJK, except in that one, in R3, it's going to be 1, 0, 0, 0, 1, 0, and 0, 0, 1. So you could see that this can be generalized, right? We can go to R4, R5, R6. We would just have a 1 in one spot and a 0 everywhere else. We're not going to call these I, J, K very often, or we can call it that when it's low dimensions, but we have another name for these kinds of vectors when we have a bigger vector space, okay? So definition, we call EI is going to be the vector that you get when you have a 0 everywhere except for the ith spot, and that's a 1. So what does that mean? That means that another word for I is E1, and another word for J, or another symbol for J, is E2, right? And if we were in R3, symbol for K would be E3. But of course, if you have higher than, R3, right? Like if you're in R4, then you have 4 of these. If you're in R5, you have 5 of these. We call these bases formed with these vectors, we call it a standard basis. So let's write that down. So for R2, we know that the standard basis is E1 and E2, right? Remember, that's just I and J. For R3, the standard basis is E1, E2, E3. And we can keep doing this. So for any n, the standard basis is E1, E2, all the way to En. So one note here, are we ever going to deal with vector spaces that have basis of infinite size? The answer is no. So note, we will primarily be studying vector spaces that have a finite basis. These are called finite dimensional vector spaces. So, guys, we usually use the abbreviation FDVS, finite dimensional vector spaces. Okay. So that's primarily what we study in this class. If you want to study vector spaces with infinite dimensions in detail, then these are for more advanced math studies, okay? That's not something that we do in this class. Okay, so let's keep going here. Can we define a standard basis for other vector spaces? In other words, for vector spaces that are not Rn. So the answer is yes. What you have to do is figure out what the independent constants are or the independent scalars, I should say, in each vector are, and for each one, put a 1 there and a 0 everywhere else. Okay, so this is going to be our strategy for finding a basis for vector spaces. So let's do some examples, okay? So first example. Determine the standard basis for the vector space M2 of R. So what is M2R? Remember, M2 of R are the set of all 2 by 2 matrices with real coefficients. So M2R is equal to, if we were to write it in set notation, it would be the set of all matrices that look like this, right? A, B, C, D, where A, B, C, D are all real numbers, right? Now you'll notice that there are no constraints here as to what A, B, C, and D can be other than real numbers. And so we can write out the standard basis. First, we could put a 1, 0, 0, 0. Then we could put 0, 1, 0, 0. Then we could put 0, 0, 1, 0. And then we could put 0, 0, 0, 1. And this we could call our standard basis. Actually, let me write it over here. Now, note, it doesn't make sense to call these E1, E2, E3, E4, because then you would have to remember which one is which. And so what makes more sense is to call this guy E11, and this guy E21, this guy oh, sorry, I made a mistake. This should be 1, 2. E21 and E22. In other words, you can see what we're doing here. Eij would be the matrix with a 1 in the ijth spot and 0 everywhere else. Okay. Now, what is the size of the basis? The size of the basis is 4, because there's 4 elements in there, right? This is going to be important. We're going to come back to this size concept later, okay? But for now, we're just writing down the size of each basis, right? So size of this basis is 4. Now, this is the standard basis. It doesn't mean this is the only basis, but this is sort of the most simple one, right? Just like the most simple way to span R3 is just with ijk, it doesn't mean that it's the only one, of course. Okay? All right, so let's do another example here. Determine a standard basis for P2 of R. Remember what P2 of R is. P2 of R is the set of all polynomials of degree at most 2, right? So recall P2 of R, if we write it in set notation, it's the set of all A plus bx plus cx squared, such that A, B, C are all real. So what will our basis be? Well, remember what I said? Put a 1 for each constant and a 0 for everywhere else, right? So in other words, our first one is going to be for when we have A equals 1 and B and C both 0. So that would be 1. Then our second basis vector is going to be when we have b equals 0 and the other two both 1. That's going to be 1x. And then the third one is going to be when c is 1 and the other two are both 0. So that's just 1x squared. Or we can also just call this 1x and x squared, right? We know that when there's nothing in front of a variable, there's really an implied 1 there, right? So we agree then, we can build any polynomial using these three vectors, right? As long as we have these three, we can build any polynomial using a linear combination. So these span the whole space. And I want you to notice that the size of this basis is indeed 3, right? Because we have 3 elements in there. So you may wonder, okay, is it true that a basis always has the same size for a particular vector space? That's a very natural question. So the next theorem and the next few things I write down are going to solidify this question once and for all. Okay, so let's look at the next theorem. If a finite dimensional vector space has a basis consisting of n vectors, then any set of more than n vectors is always linearly dependent. Okay. So I'm going to give an outline of the proof. I'm not going to write every little detail of the proof, but I want to give enough detail that you can understand why this holds. This is a very important proof in the terms of linear algebra to understand how proofs work, okay? So I don't want to deprive you guys of this. So here's what we need to do, right? We need to take any basis and show that if you have more than m elements in that space, that they must be linearly dependent. So let's suppose V1 all the way to Vn is a basis for V. And now let's take any m vectors in V with m is larger than n. So let's suppose that we have more than n vectors, okay? So, since this guy is a basis, it spans V, so each Wi is a linear combination of the VIs. Okay? So you can take each W and write it as a linear combination of the V's. Okay? So let's keep that in mind. And what we're going to do is we're going to look at this equation, right? This is the linear combination, right? We're trying to show that there exists a non-trivial solution to this, right? So this is our linear dependence relationship. However, by what I wrote down a second ago, we know that each W can be written as a linear combination of all of those, right? So we actually need double subscripts for this. So I'm going to write it like this: A11 V1 plus A21 V2 plus all the way to AN1 VN. And we continue this pattern. The last one is going to be WM, right? Because remember, there were M of them. And this is going to equal A1M V1 plus A2M V2 all the way to A NM VN. Okay? So what I'm going to do is I'm going to replace. Now, actually, before I do the replacing, let me write this using sigma notation, okay? So each W is going to equal A, so this is AI1 VI, and all of them can follow that same pattern. This is going to be AIM VI. Okay, and the sum, of course, is going from 1 to n. Now, here's what we're going to do. We're going to take this dependence relationship up here. So this guy right here, we're going to rewrite it, except I'm going to replace each W, which we know is right there. I'm going to replace it with that sum. In other words, I'm going to take that equation and write it with V's instead of W's. And so this is what it looks like. C1 times AI1 VI plus C2 AI2 V2 all the way until CM AIM sorry, that should, from before, that should say VI. I apologize. These are all VI, right? Because they're summing over all of that. Equals 0. Okay, now, I hope you guys understand what's going on here, okay? We now have this relationship, and I want you guys to look at this. How many equations, if we collect like terms here, understand that we only have M unknowns, right? M unknowns, because the unknowns of this are C1 all the way to Cm. But how many equations are we going to have? Well, we're going to get an equation from the V's, right? By setting components equal to each other after collecting all the like terms. So this is going to be N equations. Okay? So what does this mean? We have an N by M system. But remember, guys, M is larger than N. And the system is homogeneous, right? Sorry, I forgot to write that this is the 0 vector. So what does this mean? This means there must be a non-trivial solution for the CIs. And so W1 until Wm are linearly dependent. The reason I call this an outline is because, of course, I didn't write out the whole system. It would require a really technical breakdown of how this turns into the system, okay? But all you would need to do is basically write it all out and then collect all your like terms and write it as a system of equations. But we know the important thing to remember here, guys, is that we know that we're going to have something. It's an n by m system, but m is larger than n. So it's going to look something like this. And we know that we're going to be forced to have some free variables, okay? There's going to be some free variables because you have more columns than you have rows. And that's the reason why. So that's the outline of the proof to this. If a finite dimensional vector space has a basis consisting of n vectors, then every spanning set for V must contain at least n vectors. Okay. Thus, the number of vectors in a basis for a finite dimensional vector space is fixed for V. This is super, super important, okay? What we're saying here is that in order to span, you need to have at least the number of vectors as there are in a basis. But the theorem before says that in order to be linearly independent, you need to have at most n vectors. Okay? So this means if you have any more vectors than you have in a basis, you can't be linearly independent. And this corollary says if you have any less vectors, you can't span the whole space. So this means we have a special number now associated to every vector space. You can imagine what we would call this number. We've been using this number loosely. We call this number the dimension of a vector space. The dimension of a vector space V, which we write as dim V, like this, is the number of vectors in any basis for V. Number of vectors in any basis for V. Okay, so now we know what we mean when we say that, for example, R2 has dimension 2. It's because any basis for R2 has exactly 2 elements, or 2 vectors. Our only exception, and this is just a weird one, okay, but this is just something we should remember, is that the dimension of the trivial vector space is just 0. Okay, that's our only exception. Because yes, if you put 0 by itself in a set, it's its own little tiny vector space. Sort of like thinking about the point, the origin, right? In other words, R2 is the whole plane, R1 is just the real line, but this is like, you can think of it as R0, right? It's not called R0, so don't, officially think of it as that, but yeah, that's basically what it is, right? It's just literally one little dot, and that's it. Okay? So, example. What's the dimension of Rn? Well, we know that we already found a basis for Rn. It's E1, E2, all the way up to En. So the dimension is always just n. So now you know what it means when we always say R2 has two dimensions. We know an exact mathematical definition for dimension now. Let's think about some more examples, okay? What is the dimension of Pn of R? These are polynomials of degree n. Well, before you blurt out a number, let's look at this last example that we did, and this will help you think about this. Okay, remember for P2R, we had dimension 3. What would it have been if it was P3R? Well, then a basis would be 1x, x squared, and x cubed. Our dimension would be 4. In other words, the dimension is always one more than the n. So that means the dimension of PNR is n plus 1. It's because we have an element for every power, including the power of 0, right? That's why we get that plus 1 there. What would the dimension of the set of 2 by 2 matrices be? Well, we already did an example here. When we looked at this example earlier, we had 4 elements in there, right? So we know that that dimension was 4. But how would we generalize this to Mn of R? Remember, these are n by n matrices. So think about it. We basically had a basis vector associated to every ij spot, right? So all we really need to do is count the number of spots in the matrix. So an n by n matrix has n times n, or n squared spots. So that's going to be the dimension of that vector space. What about any m by n matrix? That's just going to be m times n. Okay, so let's keep going, okay? We have a very nice theorem. If the dimension of V is n, then any set of n linearly independent vectors in V is a basis for V. Okay. This is really, really, really nice, okay? This is basically saying that as soon as you know the dimension of a vector space, then that means that anytime you have that many of linearly independent vectors, it must also be a basis. Okay. Why is this nice? Because normally to show something is a basis, you have to show that it's linearly independent and that it spans, right? That was the definition for being linear independence. However, if you know the dimension of the space already, you basically only have to show one of those two things. So let's just do a quick example here just to demonstrate the power of this theorem. Verify that 1 plus x, 2 minus 2x, 2 minus 2x plus x squared, 1 plus x squared. Verify that that guy is a basis for P2R. Now, of course, we're going to use the fact that we already know the dimension of P2R, right? The dimension of P2R is 3, right? Because we know, we already wrote down a basis for it. Now, we're trying to verify that this set right here is also a basis. Of course, it's not the standard basis, but we need to show that those 3 polynomials somehow span the whole space. So how do we do that? Well, we can just show that they're linearly independent, right? By the last theorem, since we have 3 of them, by the theorem, or let me actually just start by showing that they're linearly independent. So we show linear independence. How do we show that they're linearly independent? We're going to create a system, or not a system, sorry. It will turn into a system, but we're going to write out the linear combination, right? C1 times 1 plus x plus C2 times 2 minus 2x plus x squared plus C3 times 1 plus x squared. And we're going to set it equal to 0, right? And what we want to do is figure out where this is true. And so we know that this is going to turn into a 3 by 3 system, right? 1, 1, 0, 2, negative 2, 1, and 1, 0, 1, right? So we know it's going to turn into that guy, 0, 0, 0, and we want to solve this system, but we don't actually need to solve the system. We just want to see that it has, or verify that it only has the trivial solution. So since it's 3 by 3, we can use determinant as a shortcut. Okay. So let's go ahead and do the determinant of this matrix. 2, negative 2, 1, 1, 0, 1, right? Oops. So I'm going to expand on the first column because we have a 0 there. So this is going to equal 1 times negative 2 minus 0 minus 1 times 2 minus 1, which is just negative 2. What do we get here? Negative 2 minus 1? Yeah, which is negative 3, which is not 0. What does that mean? This means we only have the trivial solution. Only have the trivial solution. I'm running out of space here, so I'll write it on the next page. We only have the trivial solution, so this means they are linearly independent since the size of B is equal to 3, which is the... actually, did we call that? We didn't give that set a name. How about, let's just call it S. Okay. Okay, so since the size of S is 3, which is equal to the dimension of the vector space, and S is a linearly independent set, the theorem tells us S is a basis. S is a basis for, let me be specific here, P2R. Okay, we have one more theorem. I said this earlier, but I didn't write it down, so I just want to write it down so that we've got it. Theorem, if the dimension of V is equal to n, then any set of n vectors in V that spans V is a basis for V. So once you have the number of vectors in a set that's equal to the dimension of the vector space, then that means if it spans, it must be linearly independent also, or if you know it's linearly independent, it must span also. You only have to check one of the two basis conditions. So this is nicely laid out in the corollary I'm going to write next. So corollary. If the dimension of V is n, and S, going from V1 to Vn, is a set of n vectors in V, then the following are equivalent. This is just putting everything together, okay? S is a basis for V. S is linearly independent. S spans V. So as soon as you get one of these three things, you get all the rest. That's what it means for the following to be equivalent. It means they all imply each other. When one is true, they're all true. So you can prove the easiest one. These are the ones, of course, that are shortcuts, right? You want the reason this theorem is useful is for conditions 2 or 3, right? If you only have to show linearly independence and then you know it also spans, or you only need to show that it spans and then you also know it's linearly independent. So think of a basis as being the smallest set that spans, but also the largest set that can be linearly independent. Okay, so let's write down some final results here to kind of summarize everything. Summary of results. Suppose V is a finite dimensional vector space. The dimension of V is n, and let S be the set of all vectors, or not all vectors, sorry, the set of k vectors. So let S be a subset of V. We're going to make a little table that's going to make this stuff easy to remember. So if k is smaller than n, otherwise, or what I mean is, so we're going to take cases here. What's going to happen if k is smaller than n, or if k is larger than n, or if k is equal to n? So if we have less than n vectors, in other words, if the dimension is n and we have less than that number, can it be linearly independent? Maybe. Can it span? No. So can it be a basis? No. Okay. Now, if k is larger than n, in other words, if we have more than the dimension vectors, is it linearly independent? No. Does it span? Maybe. Is it a basis? No. Finally, if k is equal to n, in other words, you have the same number of vectors and you have dimension of the space, the answer to all three are maybe. And the last theorem tells us also that in this very last case, these are either all yes or all no. Okay, that's what the last theorem tells us. I think it was the corollary. So by the corollary. This is just, you don't have to write this down as part of the table, but I think it's interesting to note here. That's only for this last case, by the way, where k is equal to n. Okay. Now, as another corollary, how does a subspace relate to the vector space? How does the dimension of a subspace relate to a vector space? So let's let S live inside of V be a subspace. Remember now, we're not saying a subset, but a subspace. In other words, it's its own vector space. Then the dimension of S is less than or equal to the dimension of V. Okay, so if you're a subspace living inside of a vector space, it makes sense, I hope, that the dimension of that space cannot exceed the dimension of the whole space. It must be less than or equal to it. So, as an example, what are the subspaces of R3? So let's think of the different subspaces. First, we could look at the span of the zero vector, which is just the zero vector. And this is literally just the origin. And so the dimension of S is, 0, right? The other case is, what if you take any vector that's not the zero vector? How about we just take one vector, V? Then this is going to be a line through the origin. And so its dimension is going to be 1. Why is the dimension 1? Because there's only one guy in the basis, okay? There's one vector in there. What if you have the span of two vectors, v1 and v2, and they're linearly independent? Then you get a plane, right, containing the origin. And the dimension is 2. And finally, what if you have the span of 3 vectors and they're all linearly independent? then you get all of R3. And so, of course, the dimension of S would be 3, right? Because it's all of R3. So every single subspace of R3 has to be either the origin itself, a line through the origin, a plane that contains the origin, or all of R3. There are no other options for subspaces of R3. It's worth noting, too, that this is how another reason we know that any line that doesn't contain the origin can't possibly be a vector space, right? Because these are the only options here. And we knew that anyway, right? Because every vector space contains a zero vector, right? We're almost done here. We've got just a few more last results that we need to write down. So theorem. Let S be a subspace any basis for S can be extended into a basis for V. What would the outline for the proof of this be? So let's suppose that you have a basis for S. I'm not going to go through this whole proof, but let's say that we have a basis for S, and let's suppose that that would be V1 all the way to Vk. And let's suppose that the dimension of V is n, where n is larger than k. Okay, so how do we extend this into a basis? Well, all you need to do is say the following. You can create sort of a loop here. So you could ask a question. First off, does S, or does the span of S equal, does the span of this set equal all of V? I should say that n is at least k, okay? So does the span of this guy equal V? Okay? If yes, it's already a basis for V, and you're done. If no, choose any vector and call it Vk plus 1. Not in the span, because if it doesn't span the whole thing, then that means you can find a vector not in there, right? So you could choose any vector not in the span of S, or no, not the, okay, you know what? I know why I'm confusing myself here, because we called S the subspace, but then notice here I said S was that set. I shouldn't have written that. So let me just fix this problem really quick. The basis for S is this set. Okay, I shouldn't call that S, right? Okay, is not in the span. So choose any vector not in the span of the set, and then add it in, and then you repeat. So I'm hoping that makes sense. So what happens is the following, right? Each time you ask yourself, does it span the whole thing, your subspace? If the answer is no, then choose any vector that's not in there, stick it in there, you've made it one bigger, and then you ask the same question again. Does it span the whole thing? If the answer is yes, you're done. If not, find another guy that's not in there. It must exist. Stick it in there. And you could just keep doing that, and that will allow you to extend it into a basis for V. And so that is the outline for this. Okay. So let's do one last example, which will be a fun one. We get to practice this idea. So example, let's let S be the subspace of symmetric 2x2 matrices. First, find a basis for S. Then, find the dimension of S. And then finally, extend to get a basis for M2R. Okay. Now, remember, we have to start by writing out the definition of S, okay? Remember, S are the symmetric 2x2 matrices. Remember what it means to be symmetric? It's the set of all A in M2R such that A transpose is itself, right? But for 2x2 matrices, this would be the set of all matrices that look like this. We have A, B, C, C, right? The only way that a 2x2 matrix can equal itself is like that. So it's a set of all matrices where A, B, and C are real numbers, okay? So we can see right there that there's actually only 3 independent choices for real numbers, aren't there? And so we could start with the obvious basis for S, which would be, got to be careful here. A basis for S would be 1, 0, 0, 0. And then 0, 0, 0, 1. And then the third one will be to let C equal 1, which actually gives us 0, 1, 1, 0, right? So that would be a basis for S. So we're done with part A. So part B, it says find the dimension of S. Well, all we have to do is count the number of elements in the basis that we found, right? So there are 3 elements. Okay. So we're now on part C, which is to extend this basis to get a basis for M2R. This may seem like a daunting thing here. How on earth can we find something to extend this with? But here's the nice thing. The nice thing is that we're actually really close to getting the whole space, right? And let me explain why. We know that S lives inside M2R. This guy has dimension 4. Remember, 2 squared. 2 times 2 is 4. And this guy we just found has dimension 3. And so really, all we need to do is add one more matrix into that set, and then it must span the whole thing. But we need to make sure we add something that's not already in the span. Okay? But this is easy, right? We can just choose any 2 by 2 matrix that is not symmetric. It doesn't matter which one we pick. Any one will work. Okay? So, which one do we pick? Well, the easiest one I can think of is maybe something like 0, 1, 0, 0. That's not symmetric, right? Or actually, maybe we'll put a 1 in the upper right corner. How about 0, 1, 0? It doesn't really matter. The point is, notice that that guy is not symmetric, right? This guy is not symmetric, because if you take its transpose, you do get a different matrix. And so that means that if I take my basis from before, 1, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, and my new guy that I just came up with, 0, 1, 0, 0, this guy, since there are now 4 elements and the dimension is 4, this guy must be a basis for M2R. Now, obviously, there's not a unique answer here. Another thing to note is that if the dimensions had been more than 1 away from each other, then this would have been a harder problem, right? Because we would have added 1, and then we would have needed to figure out something that's not in the span of the new basis, which would be a more complicated question. But this was pretty straightforward here, right? All right, everybody, that's it for this section. Thank you so much for watching.